has done his PhD from Indian Institute of Technology, Jodhpur in Electrical Engineering Department. He has received his ME from PEC University of Technology, Chandigarh in 2011. He has published many papers in reputed journals and international conferences. He received many research fund proposals for various organizations, university too. He has organized many workshops in the area of RF, microwave and communication. He is a member of IEEE Society and MTT Society. His research area includes ultra-wideband USB antennas, MIMO antennas, antennas for 5G, IoT, artificial intelligence in electromagnetic, machine deep learning in RF circuit design, energy harvesting, radar, and signal modulation demodulation techniques. Welcome you, sir, for this session. Over to you, sir.
Thank you, Dr. Sarthak here for giving such a wonderful introductions in front of audience. As well, once again, thank you to you again here for giving me an opportunity to have interactions with all the peoples here and the audiences here, so that whatever I have learned in this domain here, I could share with all of you here. So my PPT is visible to all of you?
Yes, sir, it is visible.
Okay. So thank you. And meanwhile, once any interruption is there, then just let me know, or any place if you feel you are not able to understand here, feel free to interrupt me here at that instant here. So before I start, once again, a very good morning to all of you here, and welcome you all in this very wonderful session, which is the need of the time for today's generation here, explicitly for the people who are working in the RF and microwave domain here. Because once we talk about the application of AI in the RF domain here, this is something many of us don't feel so much comfortable, because it's slightly uh, orthogonal to the areas which we are working it here. Because whatever the history or legacy we have here, in this legacy part, a lot of computational aspect is required, as well as a lot of understanding at the core level, concept level is required here for one to understand. Because comparable to the other areas, if someone willing to explore it here, and then even they have some expertise here, they can explore it here. But explicitly working in this RF and microwave domain, you have to be good in both the domains here. You should be very good in the RF and microwave domain here, as well as in case of application of these tools for the optimization part here. So I will try to connect these two domains explicitly in case of antenna circuit designing part. So before we start, just have a very quick review related to the antennas once we started here. Then in general, once we talk about the antenna system, this is the device which is converting the energy from one form to the another form here. So we can say electrical signals, voltage or current to the electromagnetic signals here, and vice versa here. And generally we use some metal wires or strip in the form for the any structure to have the radiation characteristic here. And once we go further deeper here, then generally two ways these propagation used to happen. One is through the guided electromagnetic wave, and another unguided here. Once the transmission is happening through the air, then it is comes into the category of unguided. Once it is happening through the some metallic wire or strip here, transmission line or the waveguide here, then it is called as the guided electromagnetic waves here. So, but ultimately we are going to deal about the electromagnetic waves here, as well as the circuitry which is responsible for the generation of these EM waves here. So these will be our agendas for the discussion. And before we start the application part here, let's try to understand the complexity involved in the system. That's why many people are slightly away of applications here. And once we talk about any structures, the radiation characteristic here, then we generally used to say that there should be a time varying current in the nature here. There should be acceleration or deceleration of charges, as well as some spatial imbalance is required so that radiation phenomena can be induced here. Once the radiation phenomena is induced, then the EM waves will be generated here. And in any medium, when we want to analyze this electromagnetic waves behavior here, then we have to deal with the Maxwell equations here. So those who have worked it either in conventional approaches, in earlier there was a numerical methods being used so explicitly here. Then with the advancement in case of semiconductor devices, or you can say in the form of computers, workstation, high-end computing facilities, we used to move towards the simulators here. But even if you go in the inside the working of those simulators, there will be certain algorithm solutions which will be present here, which will be responsible for overall computation here. So what were process we are doing earlier in the manual way, those things is being performed by the machines here. So in all such cases, at the backbone there will be a Maxwell equations here. That is the baseline for our discussion here. And once we go ahead for the use of the technology, then once we talk about the AI, then the artificial intelligence, which you are talking about here. So the basic question arises how we can bring the intelligence in the system level designing here. Because what is system we are going to design it, how we can use the conventional approaches, what we have already aware, so we have good in that part here, can be mimicked in our advanced technologies tools here, like artificial intelligence, machine learning, or deep learnings here. So in all those cases, we are going to understand today's session the basic framework of these algorithmic solutions here, and then we'll try to understand what are the opportunity for persons who is working in the RF and microwave domain can explore these things explicitly. So once we talk about the algorithmic part here, so AI is being inherited from a broader structures or a broader umbrella of the computer science. Then machine learning has many subclassification where self-supervised learning, supervised, unsupervised learning, reinforcement learning, and there are some common areas within that where we formulate the concepts of deep learning here. So ultimately, whatever the technology terms related to the optimizations we are going to do, either regression techniques or supervised KNN, ANN, CNN, or any other like this here. So we are going to talk in the broader spectrum of the artificial intelligence here. So all these techniques are the part of these techniques. So everyone is slightly different in terms of modality, their working framework here. So based on the nature of the input, we are supposed to adopt any one of them here to our problems here. So before we start the exploration of artificial intelligence in our antenna design here, let's try to understand the framework where the possibility exists for us to apply these kinds of tools here in case of antenna design. So if we go a little bit in the history and connect with the previous approaches here, then we can understand very easily there is a huge possibility for us to apply these techniques here very easily in case of antenna design. And if we read few of the older papers here, then we find a lot of work has been done here by using the computational electromagnetics. This is the area which we were aware it here in the past. So if we go in the details, so everywhere we will be using the Maxwell equation either in the differential form, the integral form here, in the different medias or different situations to solve the problems here. It could be related to the linear antennas, it could be the dipole antennas, or etc. etc. here. Here. Or antennas array cases problems here. So ultimately we'll be dealing the Maxwell equation, only the methods will be keep on changing in the time frame here. So the method of moments was very popular method here, and other methods if we see the numerical method, high frequency methods, correct, and transmission line based method here, FDTD methods here, differential equation based, so field based methods here. So we have a large numbers of the computational techniques which have been used in the past years to optimize such kinds of radiating structures here. The only difference you can find out applications here. Earlier, we will deal about some of the radar system here, because if you go in the centuries ago, even the First World War around here, the Second World War around, if you see, there was already the concepts of radar system here. So people were designing such kinds of complex system for the different purpose here. And that time they don't have the such kinds of high-end computational facility. So obviously these kinds of methods were coming to be very handy for them in optimization the structures and then the designing part here. And later on in the evolution part, once we move ahead, then we comes with some very good simulator here, which we are using most of us, HFSS, EST, ADS, IE3D here. So if you go in the basic framework of these softwares here, then we can find out at least one of the techniques is there. Based on these techniques, this technique is being used for the optimization part here and the basic framework somewhere here. So in this evolution part, there is one very interesting steps comes here when the genetic algorithm comes into the pictures here. And if we go in the optimization history, then we'll find out a lot of work has been done based on the genetic algorithm here. So what was so specific, or you can say special, about the genetic algorithm that has given the advancement compared to the other techniques here? This will be one of the part we'll be also covering in the today's session here. So once we are looking at the history, so many approaches have been introduced by the peoples here, and the major breakthrough is comes when the genetic algorithm comes into the pictures here. And the basic framework for the genetic algorithm is we used to formulate objective functions here, and through the objective function, we used to find out what will be the associated minima or the maximum of the equations here, and based on that, we'll try to solve the best possible solutions here. So whatever the characteristic we are looking forward, corresponding that characteristic we want to formulate objective function, then we'll try to solve it here for the proper structures here. So if you see in the history part, then most of the work related to the genetic algorithm, or as well as the previous techniques, if you find out here, will be relying on the antennas array. So approximately 60 to 70% work in the past, if you find out, it will be relying on the antennas array structures here, because the antenna arrays have been used so predominantly into the radar system here. In the earlier cases, radar was the very promising application which is being explored by many of us in the RF and microwave domains here. Here just for the working purpose. So with the evolution, other applications comes here, but the earlier session was totally based on the those specific aspects here. And if you are interested to learn this domain here, so what we are trying to do it, we are going to learn it in a step by step manner here. It is just like that. If someone want to run, then our approach will be we should learn first the walking. So similarly, if I need to understand a complex situation uh, of use of AI tools in the antenna design here, then our basic strategy will be to uh, go ahead with the basic parameters of the simplest kind of situation, where we can understand how these frameworks can be used here. Okay? So we are considering the sample case of the antennas array, and then in case of antennas array, we are trying to learn how the optimization process is evolved here. Okay? So in this evolution process, our objective will be again, just as we have discussed, our first aspect will be to formulate the objective functions here. Once you formulate the objective functions, then the rest of the optimization process, in case of genetic algorithm or any other algorithm, we used to apply it here. So the first thing is, once we talk about the antennas array, there are certain aspects related to the antennas array, related to the optimizations. First is the inter-element spacing between the two antenna system. we can optimize what is the amplitude I am feeding is to those antenna system, one aspect. Second is what is the associated phase with them here. So these three parameters are going to be very crucial in any antenna array system optimization part here. And once we are talking about overall efficiency of the structures here, then we also consider what is the incident angle of the wave. So that based on the incident angle of the wave, how much power is going to be converted efficiently here or the transmitted here, this can be decided here. So in general, once we talk about the antennas array optimizations problems here, many places you will find out intermittent spacing, amplitude, and the phase here. So amplitude and phase, what we are talking is related to the power feeding, because we all know that antenna is a passive device. So it will not start radiation by itself until unless I'm not going to feed the power to it here. So keeping that part in mind here, amplitude as well as the phase. So whatever the numbers of elements are present there, correspondingly I can change the amplitude, I can change the associated phase also here. And other parameters, what we are talking, the space, inter-element spacing it here. So theoretically, I can say there's has a lot of possibility for me to explore it, but practically, once we go for a designing purpose here, generally we keep the distance less than lambda by 2 here. So that's the reactive energy is not going to be very much a problematic for overall functioning of the system here. So generally it is lambda by 2. So from a overall design optimization perspective, once I look at the parameters here, so d is something, or you can say distance is something which is not so much tunable parameters, which we can give the wide versatile results possibility here. So but amplitude, phase, two parameters are still with us, which have the total tuning capabilities for us. And second part is related to the angle of incidence, that is the phi. So with this understanding, we are moving ahead in case of optimizing one variables here. So once we go for the optimization part, as we have discussed, the first thing which we need to learn is will be the objective functions here. For the objective functions, we are considering the present case where it is a function uh, given in terms of amplitude and phase, and certain values we have considered just for sake of simplicity. So once we solve these equations here by some numerical method, so we are coming out towards the value, and here you can find out the value is x-axis. You can find out. So here you can find out the value is u is equal to in this range 0.4 to 0.6. So you can say approximately 0.5. Somewhere it is converging it here. So when we go for the optimization part, so we all know that optimizations can be done either way. Either I look for the maxima or I can look for the minima here. So in a conventional approaches, finding the minima is much more convenient compared to the maxima, because once I equate the value to the minima, that's a zero most of the cases here. So I can find the solutions, or the equation becomes slightly easy for us to solve it here. That's why minima part is preferred here most of the cases. In our discussion, we also emphasize towards the minima. Once we solve it, these values here, then we are going to find out u is equal to 0.8. If you remember, previous case u was equal to the cos phi. So based on the angle of incidence, the value of v is coming it here. So how the value is varying? So that's why x-axis, if you observe, this is maximum from here 0 to 1, because cos phi, cos value is going to be minus 1 to 1. So one part I am considering here for the reference. So it is 0 to 1 maximum here. And the maximum amplitude we have considered as a unity here. So that's why y-axis is limited to the 1 here. And once we are going for the optimizations, then we comes to the final values. A is equal to 0.382. What was coming to the first stage as a 0.4, 0.5 approximately here. Second is First part was related to the amplitude. Second part's tuning, I can go ahead with the phase here. So similarly, I have to formulate the objective function first based on the phase variations here. So this finding objective function is not a very hectic task. Whatever the input we have, based on those inputs, if we give to some of the mathematical simulators here, even the MATLAB or the Python's based environment here, we can always find out what will be the relation between them here. So defining the relation between the parameters is, we are calling it as a objective functions here. So we are considering in case of phase, will comes out with an expression that is the objective functions. The objective function f2 is written it here, and there is a basic difference once I am going for the optimizations based on the amplitude and based on the phase. Because once I am going for the amplitude here, in case of amplitude, generally we have certain steps we consider here. For example, 0.25, 0.5, 0.75, 1 or something. Generally, it is based on those power level generation it here. So generally, we used to keep it those intervals in the power level, and accordingly we used to proceed it here. But once we comes to the phase level here, phase have the capability to tune from 0 to pi. So 0 to pi, if we see the range of possibility in terms of phase here, so that is much more compared to the amplitude level variations here. So that's why once we go for the optimization part here, the input which have the more uh, versatile nature in terms of number of values possibility, or you can say number of input possibilities here, is considered to be more appropriate parameters for the optimization purpose here. So even in the case of optimization, once you explore here amplitude and phase, phase part is going to be much more random, as well as much more compatible parameters compared to the amplitude here, or you can say handy parameters here compared to the amplitude part once it comes to the objective functions here. So based on that, we have simply drawn a numerical analysis based on the relation. So here we are considering the two minimas. One is close to the here we are getting, another minima we are getting in this point here. So once we have the two minima, now we are going to trying to mimic it with the help of the random search algorithm here. So once we are going with the random search algorithm, then there's a possibility to look these aspects with respect to the futuristic possibility, how we can integrate the AI part here in the circuit design level here. So the first is if we take the example of random search in this optimization part. So how this values we can find out or convert so quickly here in terms of optimizations. So first one is here we are observing. Here you can observe some of the values which is already present. Okay, is given here, and similarly for the other case f2. In this cases, just try to focus the values in case of amplitude based at the point 4. Our values are point 4 in case of random search algorithm here. Those you have already worked it. So all of you are already aware that random search work based on to in a totally random manner here. So inputs are being selected random manners here, and certainly based on the next value which we are considering to accept it here. For that purpose, I need to select the values here, not in a random, but based on the gradient here. For example, once we are going towards the minima part here, so minima part is always towards the downhill. If I check the value, one set of values, if I'm getting this values here, right? For the next set of values, if I'm getting the values like this, correct? So it is come something like a downhill search. So going towards the negative of the gradient here. Once I am moving towards the negative of the gradient, it means I am converging the function value towards the minima here. But at the same time, if I am going upward here, correct? Then I am moving away from the minima here. So that's why once I'm selecting the value in the random search, next values are which is being opted here, considering these possibilities here. So these possibility will give me the chances to select the proper minima here. So even in the first 10 random selected points here, you can observe in case of amplitude, 2 points are coming very close to the minima in case of amplitude, that is close to the point 4. Similarly, in case of phase, if I consider, 1 point is coming very close to one minima here. In other 2 points are also in the close proximity of the minima here, second minima here. So even with only few 10 samples of the random search, we coming in the close range of the minima here, correct? So that is the major breakthrough in case of random search here. So even if you go in the optimization history, you will find out the random search before the genetic algorithm, random search was very much accurate, as well as a very popular techniques for the optimization purpose here. Because prior to random search, many of the techniques which is being used by the people, they were very slow in the optimization process here. So these advantage comes in the favor of the random search here. Now we are moving towards the multiple functions variable, because we already explored the one function variable. Second, we are going for the objective function, the multiple variables here. In case of multiple variables, two cases I am considering. One is related to the amplitude. Earlier case we have considered the amplitude is constant. So here we are considering AF3, that's A1 and A2, two amplitude I am considering. Similarly, in case of phase, I am considering the two phase values, lambda 1 and lambda 2. Whatever the range of amplitude possibility we have considered in the previous case, same possibility I can assume it in the present case too here. But as the variable have been increased from 1 to 2, so obviously the complexity of the optimization is going to be much more. So here that's a graphical representation for the multivariables problems, where d phi, here you can see phi, the angle phi is still same, but only changes this part here. Okay. So where amplitude and phase I am tuning it here. So still the basic baseline is intact. That's compared to the amplitude, phase is more random in the natures here for the input possibility perspectives here. So those things will be observed here. Once we solve the objective functions here, return the sum of the magnitude phi m 120 degree, 69.5 degree, and 31.8. So multiple possibilities, multiple parameters will give the more and more possibilities in terms of minima here. Then our job will be first to find out the minima, then go for the global minimas here. Similarly, once I plot the objective function for the amplitude, we are getting the one global minima part here, and that is reflected here in this graph. So plot of objective function, that is AF3, that is for the amplitude part here. The moment I switch to the phase part here, now in case of phase, you can see the number of minima possibility. Multiple minima is coming it here. The reason is, again, I'm emphasizing again and again, because once we go for the algorithmic solutions, for especially like the AI, machine learning, or the deep learning here, the random nature of the input is going to more suit to the optimization's nature here. So more and randomness, more and more accurate and reliable predictions you can expect it from that system here. The input is like that. So still we can observe in case of objective functions, multiple minima we are obtaining it. So still, what was the basic time frame with respect to the previous technique? That most of them were still time consuming it here. They were not conversing very quickly here. Whatever the optimization's problem or the slope they were following, it is going to take a lot of time here, as well. The perfection in case of finding the minimum was not so convenient here. So then people comes out with a very beautiful ideas. Okay, that overall they were just nice. The overall optimizations scenario, that was the simulated annealing here. That's very simple concepts. If once we discuss it, all of you will appreciate it. That's how the simple concepts help in overall optimization scenario to change it here. So what was the case here? Because once we observe the nature, how the nature is following the overall optimization problem here, right? So once I am considering that substance is there, material is there, which is close to the 100 degree here. If I want to cool it here, so that cooling part is going to be in the abrupt minutes from 100 to 90, then 80, then 70 or 60, like this here. We all know that answer is no. It is not going to cool in that manner here. It is going to follow the process that's very gradual as well as uh, influenced by the nature parameters here. Okay. So here the nature is helping us in finding the optimal solution based on the atmospheric temperature. The temperature of that material is going to be cooled down to that level. For example, if the atmospheric temperature is 25 degree here, once it start cooling from the 100 degree or 90 degree, it will comes and settle down to the 25 degree here. It will not come slowly to the 0 degree here. It is not going to be possible. So how the optimization process once we are going for any scenario or any applications here, up to what extent I need to consider it, up to what extent I need to consider the optimization or the convergence of algorithmic solutions here. All these parts can be understood very easily, very conveniently here by the simulated annealing examples here. Okay. So the question was, once we have the simulated annealing, means the optimization process inspired by the nature here, it becomes much more convenient for us, okay, to connect with the nature, and also the reliability or robustness of the solutions is also enhances it here. Okay, but at the same times we want solutions to be more and more quick. And what was the most appropriate fast algorithm which we have came across in the previous optimizations history discussion? That was the random search here. So the idea was, if we can design something which is inspired by the nature, like the simulated annealing here, as well as have the quick nature of the random search here, then these kinds of algorithmic solution is going to be more and more appropriate for optimizing the solutions here, because the solutions of the scenario which you are going to talk it here is very complex, that is totally relying based on the Maxwell equations, and those who have solved the Maxwell equations even for the basic structures here, they can have the idea how competitive or the complex it is here the moment you start solving it here. In case of the simple boundary cases, becomes very difficult for many of us to analyze it as well as understand it here. For the complex 3D structures, it is highly complicated to visualize it as well as to solve it here. Okay. So, taking the properties of the nature as well as the random search here, we think about the new algorithm here, that is genetic algorithm here. So genetic algorithm has been evolved by considering the two previous approaches properties that is very much suited for the overall quick optimization part here, simulated annealing. Second is the random search here. And the nature which we are considering to mimic it here is the biological nature here, biological systems here. That's why the name comes with the genetic algorithm. But even the core part, if you see it here, the random search as well as the simulated annealing concept, you can visualize it here. And once we have taken the genetic algorithm, so genetic algorithm came across the different processes here, like natural selection, genetic drift, mutation, migration, etc., etc. So those parts will be the part of the overall genetic algorithm. So that is not our area of concern. So from the optimization perspective, if we focus how the genetic algorithm is going to be useful for in an optimization case, then I can say, as we are going to consider a population, so the whatever the terminology we used in case of our in our surrounding here, same terminology had been transformed with the applications perspectives here. For example, we used to call it the populations. Here against the populations, we are going to formulate objective functions. Okay, and for objective functions formulation here, we need the some characteristic in terms of that is the chromosomes which is defining, and the input to these chromosomes is called as the genes here. Okay. And the objective functions, once I'm going to feed certain set of inputs here, certain set of genes here, so whatever the values I am going to get it here, we used to call it cost it here. Okay, so we can understand in a very broader perspective. Uh, there is a populations which we need to study it here. Against that population, we have defined certain chromosomes, correct? Against that, those chromosomes here, the values comes in the form of genes here. That is the input part. Okay, and using the chromosomes, we used to formulate the objective functions, correct? Against those objective functions, once I am feeding certain values, genes values here, I am going to get a values here. That value is going to be called as the cost. So in the cost analysis, the function which is having the lowest cost is considered as the most fit. As the highest cost of values, genes here will be discarded, and the lowest cost genes value will be considered here for the round of optimization part here. So that is totally inspired by the survival theory. So the one who is going to survive is going to be retained here in the future. So in this case, if we see the mathematical parts, then it becomes much more convenient for us to connect with our antenna systems here. Here, for example, once I am considering a population here, so this population can I mimic with one of the antenna? I can say this could be antennas here. Whatever the chromosomes means, this is parameters which we are considering it here. Can I consider S11? Again, next parameter I can consider. So those who have designed the antennas, we have always come across these, correct? What about the field? Electric field, magnetic field, correct? Means I can say the radiation characteristic. I can think it. Okay. What about the gain? G. Gain. So now we can visualize. That's just like we are mimicking a populations here in the genetical optimizations here, because ultimately once you are applying these kinds of tools here, they doesn't bother what is the nature of those input parameters, what application you are bothering it. They always bother about the natures, what is the input you are feeding to them, against based on those inputs they are supposed to come out with a certain outcome here. So now if we see the overall design part, our antenna structures here, antenna system here, then I can mimic it population as an antenna system. It could be a dipole, it could be MIMO antennas, 5G antenna, IoT antenna, or any other antennas which you are working it here that you can think of as a populations here, and the different characteristic of the antenna system can be replicated or think of as a chromosome values of chromosome 1, 2, 3, 4, 5. Here we can mimic S11, S12, electric field, magnetic field, gain, efficiency, torque, fidelity, correct? So there are so many numbers, I can keep counting it here. So based on that, we used to optimize the antenna structures here. And the most important is these chromosomes values are depending on the genes value G11, G12, G1M here, right? So now once we go for the antenna, any antenna structure designing here, for example, if I consider it here, this antenna structure, very simple here. There is a circular structures. There will be, okay. For example, if I'm considering the patch antennas here, so patch antennas, what is the radius? Will be one parameters, right? What is the length? what is the width, right? What is the substrate height, what is the thickness of this feed it here, correct? All these parameters we are using it in the antenna structure optimizations here. So can we think the values of these parameters, which is genes values here? Did you understand my point? Because this is very important. If you can connect it here, then rest part is very easy to connect it here. Anyone any doubt? So you may ask it. Okay. So here we are mimicking that's the genes value of the genetic algorithm with our antennas design parameters here. So design parameters could be related to the length and width of the ground plane, your substrate height here, right? Your the feed line here. What is the radiator structures you are considering? Radiator structures, length, width, radius, etc., etc. Here. So based on the complexity of the structure, so many numerous parameters I can assume it here. Okay, and once I am considering these parameters, so whatever the S11 or S12 or electric field gain we are talking it here. For getting a specific S11 here, I need all these parameters as specific values here. This is we have witnessed it here, correct? Similarly, once I am moving towards the next value of S11 here, so keeping those same parameters, can I obtain it? And suggest straightforward, no, we can't obtain. The moment I change the S11 corresponding, the parameters value will change. Maybe all the parameters will not change. At least one or two or few parameters will be changed here. Then there will be change in the characteristic here. Either S11, S12, electromagnetic fields, radiation characteristic, or the gain values here. So once I looking forward at the framework of the algorithmic solutions which is being used it here. This framework is very much compatible or very much matching with our design system here, the conventional approach of antenna system, which we are using it here. The only task for us is to how we are going to map it, correct? So once we are going to map it properly, then I can take the advantage of these algorithmic solutions efficiency it here, right? And once we have certain set of values, I can feed to the objective functions here. Against those objective functions, we can find out the cost values, cost 1, cost 2, cost n, cost n here. Again, for optimization parts here, we used to go for the fitness values. So for the fitness part, the thumb rule is again low cost is going to gives the highest fitness here. So what were the numbers I am considering? For example, out of the n parameters, n cost function, I can straightforward I can say uh, 10 values, or I can say half of the values I am going to consider. Okay. Okay, so here we can take some values. For example, cost one values I can say it is 10 here. This is 7. This is 8. This is 4. This is 3 here. Okay, etc. etc. I have taken certain random numbers here. So here one assumption I can say is there are the chromosomes value which will be having the value more than 5, or you can say less than 5 will be selected here. For less than 5, then these two will be selected here. If I says less than 7, then the 7 will also be selected it here. If I says only, okay, then if I go through the 10 here, then 10 maximum I will consider this 10 here. So all of them could be selected here. So based on the number of input I am looking forward for the consideration, we used to go ahead with that part here. Similarly, in case of design part here, once you're going for the designing part here, does we consider the parameters like what is the color of the substrate here, okay, which is the manufacturer of this substrate, the company manufacturer, okay, because this is not going to be very much helpful here. What is the simulator softwares I am using it here, correct, in the design part. So it doesn't matters here what is the PC configuration microprocessor controllers I'm using it here. All these parameters is not so relevant related to the radiation characteristic of the antennas here. So if I'm introducing certain uh, irrelevant parameters here, these parameters can also be sorted out here in the iteration. They will immediately, because they're not contributing it, so we can always discard them here. And these things can be find out very easily based on the cost analysis here. So many times, once we go ahead with genetic algorithm optimization problems here, they are always working with the numbers here. So if the numbers is not there, we can always take the help of random numbers here, the random process concepts here, where corresponding certain inputs of any experiments input here, we can always map it with the values. Once we have the values, then genetic algorithm can work is very efficiently here. And we have just discussed for the absolute number of binary representation, this genetic algorithm can be expanded towards the binary number representation here. So what are the values we have considered? For example, if we consider the previous case, okay, there are up to 10 I'm considering. So up to 10 if I consider, for example, if I have to write 3, same number binary representation 0, 3, 1, 1, correct? For 4 if I consider 0, 1, 4, 4 it here. Okay. So once I am converting from the absolute number to the binary number, just please try to understand the importance of this conversion it here. Once I convert from the absolute to the binary numbers here, now we have the four possibilities, for four places for me to change the values here. Out of 0011 in case of 3, or 0100 in case of 4, I have the four places to change the values it here. So any arbitrary changes or random changes if I want to introduce in the values here, I can go for a change in these values and I can change it here. But in case of absolute numbers here, I have only one position to change. But the moment I comes to the binary number representation here, the possibility for me to change it becoming much more here. So that's why binary conversion, if you compare the results, absolute optimization as well as the binary conversion based optimization. So many places you'll find out here the binary conversion is coming to be more efficient and more reliable in terms of prediction of the results here. Those things is well proved in the literatures here, and you can also cross validate it here. So the idea is, once I am going the genetic algorithm, we have the two ways to optimize it. One is either I am going ahead with the absolute number based optimizations. Okay, either we can second approach is either I can go ahead with the binary number based representation here. In both the way, we have the proper possibility for the optimizations. We can work with the antenna characteristic as parameters, radiation characteristic, gain, etc., here, as well as the design parameters here. So we can always frame a combination one-to-one mapping here in terms of input parameters as well as the output parameters here. So this part is going to be very much helpful. Okay. And once we are going for the application part here, then application there are certain stages. Create initial population. There's the first part. Evaluate the fitness of each population numbers here. So once you go for the fitness numbers based on the given inputs, then there are further natural selections, mating, generating offspring. Okay, mutate selected members for the next round of possibilities here. So today's session, I'm not going to cover this genetic algorithm overall working part here. My idea was just to explore the framework of any optimization algorithm. Being genetic algorithm so popular, I have considered the example of genetic algorithm here. So now same things we can explore with some other algorithmic solutions. We can go to their framework and we can observe there is a possibility for the our antenna structures optimizations here, or again we can mimic our antenna design process with any of the algorithmic solutions here. There will be differences in terms of the steps difference involved in the optimization part, or their methodology part could be different here. So the graphical representations. Now coming to the second important part, how the AI is going to be applicable in this part. So with the help of genetic algorithm, we have understood very easily uh, that's for any algorithmic solutions to apply, because all these algorithmic solutions based on artificial intelligence data hungry. We need the proper data. If we can feed the data to them here, then we can expect them to work for us here. So we have to be very careful once I am formulating the data here. If you are committing mistakes in the data formulation, so it is not going to be very much helpful here. And nowadays, if you are working with any one of the simulators here, so either we talk about CST, HFSS, I3D here, so all of have the facilities to go for the optimizers. So optimizers tool is available in all the sort of simulators here. Through the optimizers tools, whatever the design parameters I am looking forward to optimize it here. Okay. So corresponding that optimization, I can go for certain parametric analysis, parametric variations, and then go for the run of the parametric tool here. So through that operations, I can generate the amount of data. Okay. So within the environment of simulators which we are using it, we have the possibility to design the framework for the any antenna structures here. So that framework will require the data, and the data part can be generated on any one of the design. Okay, based on my personal experience, I can say whatever the structures we used to take in the optimizations more than a month here, that part is done within a week here. We are not so good still in the process here. We are learning it these things here, but still our optimization process is becoming very quick here with the help of algorithmic solutions here. Okay. So once we are going for optimization part here, so let's take the basic frameworks. We are if we see the basic frameworks of these algorithmic solutions here, they are designed in the R, Java, or the Python based here. So these algorithmic framework is available to us here. I can use any one of them here, like NN, SVR, support vector regression method, Gaussian process regression, GPR. That's a base line for the deep learning based approaches here, GPR here. Broad learning system, BLS, and KRR. So all these are presented here. So ultimately, if I summarize the overall discussion, if I'm interested to apply the AI tools in any of the antenna design here, so first part is I have to work on any of the antenna design here. For example, if I talk about the antenna system for the 5G, I would be concentrating one of the bands here. For example, 3.3 gigahertz or 5.5 gigahertz or the sub 6 gigahertz. There's a 30 gigahertz range here, 23 to 28 gigahertz here, certain part here. Or someone is working for the Wi-Fi means 2.4 or IoT means 950 megahertz here. So application based frequency will change here, and based on the frequency change, design parameters will change here. So from the literature, we always get the idea what could be an approximate range of the dimension it here. Correct. So that part we can easily analyze it. If I go for reading the papers here, after reading a few papers, I can have the basic framework. What will be the desired range of dimensions for me here, and based on your approach, you can always comes out with design part here. So design part here, you need to design a basic framework, and once your the framework is ready, the basic layout is ready, you have to go for the parametric analysis. Through the parametric analysis, I can create the data set here. Once I have the data here, then I have the possibility for use of machine learning, deep learning, or algorithmic tools here. Okay, within that tools, I can go for the algorithmic solutions. Which algorithmic solution I want to check it here. Correct. Like I am looking forward for the support vector regression method, random search method here. Either I'm looking for the genetic algorithm, either I'm going for the artificial neural network, ANN, correct, KNN, or any other techniques here, correct. And once we go for the optimizations, there are certain stages in the optimization part here. related to the whatever the data I am feeding, is the model properly working or not. So we have to cross validate it first. Okay, after the cross validation, I can give the certain design outcome to the structures here. Certain design outcome is, for example, if I'm looking forward designing antennas here. So in case of S11, what the threshold we take? Generally minus 10 dB, correct? So that's minus 10 dB we used to consider. That's for any bandwidths which we are considering, for any structures to radiate it here. Then it should be the values of S1 should be below the minus 10 dB level mark here. So that's we can assume that if the structures is giving me the S1 values below minus 10 dB, then that range I can consider as a operating bandwidth is here. Similarly, once I'm designing, so when I'm working for the 2.4 gigahertz Wi-Fi bandwidth, so I would give the proper instruction to the model here. That's a 2.4 to 2.485 gigahertz bandwidth. S1 value should be minus 10 dB here. This could be one part here. Similarly, what are the S21 parameter, isolation parameter, if I'm talking about the MIMO antennas here. Okay, so simultaneously, whatever the gain I'm looking forward, give certain values to the model here. Model is going to work for us, and then it is going to help in the design part here. So as a designer, if I comment it on this entire process here, so it's totally depend on the experience of the persons here, the person who is working in this domain here, how many years he or she has spent it in this year. So based on those years learning, we are working on the design part here. For example, a very simple problem someone asked here: if there is a patch antennas, if I need to cut, uh, slot it here, so what place would be the optimal it here? What position I am going to operate here? Okay. Can you give the straightforward answer for this question? Answer would be no, because no one can give the straightforward answer. This is the place where you cut it here. So again, it is the experience of a designer. For example, if I am looking forward for a very minor tuning it here, I am already getting a 2.3 gigahertz, 2.35 gigahertz here. I will need to slightly tune it here. So obviously, I am going to put a slot where the surface current distribution is not too high here. It's a mild or the moderate level here. Where if I put the slots here, it is going to change the surface current slightly, and based on that, I can get it certain modifications here. For example, if I'm working at 2.4 and my initial results are 2 gigahertz here, then I have to select the region where the surface current density is more. Because if those ranges, if I put the alteration here, it is going to impact the drastically here. So drastic changes in the surface current path will give the high chances to get me a more change in the septic frequencies here. So these are the few of the observations once we go in the design, then we used to learn it here. So similarly, once we are going for design parameters, then validation results. So what were the parameters I am going to feed it to the system here? Based on those feeding, okay. Here, once the model predict me certain values, I need to cross validate with the simulator environment against here for the actual performance validation here. So this is the overall idea for any systems working purpose here. And then another very important part is this error analysis part here. So error analysis part is very important because based on this error analysis part, the iteration wise, we have to decide the number of iteration. In general, once we are designing in a system here, what we decide is this is the expected outcome. As for example, again, if I consider the previous case of antenna design, for the Wi-Fi, I have decided 2.4 to 2.485 gigahertz. S1 value should be minus 10 dB, below minus 10 dB here. If at the first iteration I am getting the values in minus 7 dB, minus 5 dB here, so should we accept it? Answer is no. I can't accept it because it's not giving the proper resonance here. So once I observe this resonance, so Ultimately, I'm going for the error analysis. I'm taking the difference from the my threshold desired minus 10 dB to the actual one here. What I am getting it. Based on those, I will go for a few more change in the parameters here, input level, and then I will try to find out what will be the new set of parameters and corresponding results here. So error in output will be analyzed here. Based on the high value in the errors, I will be keep going for the changes it here, right? And similarly, once I go for the optimization part here, these optimizations is very much required here at any levels, right? So if you are looking forward applications of machine learning and antenna system here, so I need to go for the first part is the simulation part, and then algorithmic applications, then for the final validations here. These are the few steps I need to remember it here. Now I'm considering few of the sample cases which we can which you have considered for our analysis purpose, as well as for you all to understand how quickly these things can be done, what would be the process of optimizations here. So the first work which we have started in our lab here for exploration, so those who are working in this domain, they must appreciate it, because this was a paper in 2020 came. It is one of the initial papers where the machine learning techniques have been used in the antenna design, and this paper gives a very nice idea how step by steps you can apply machine learning approaches here if you are looking forward to learn it here as well as explore it here. In this part, they have used some popular machine learning techniques like lasso, NN, KNN. Okay, and as the structures you can observe, it is double T shaped. So this structure is are useful for the multiband resonances here. So this structure is also giving us to the multiband resonances in the 2.4 to 3.0 gigahertz and 5.15 to 5.6 gigahertz behavior right here. So idea was, let's find out the figure of merit. There was some alternation which we have done in our lab here. Then corresponding results part. So whatever the structure was given earlier, we have replicated the design, and then we try to validate with the existing approaches which have been already proposed in the literatures, and based on those propositions, our idea was how to take the advantage of those learning and then comes out with our own learning here. So first was database creation, so where we are talking about the bandwidth creation here. So for bandwidth creations, so we have taken a very simple approach that was also formulated in this paper here. This was the figure of merit. So for the figure of merit, there's two ways to look into this part here. First is I am directly feeding the input output relations here. So corresponding to the input, what are the output parameters I am getting, I can directly feed it here. And in this work, what they have done for the certain set of input parameters, what was the figure of merit? So what is the range of bandwidth? For example, if they are considered 2.4 to 3 gigahertz, a desired one. So for certain set of values, they are getting only 300 megahertz bandwidths. So they are marking it as 300 only. For again, in next set of values, they are getting the bandwidths 400 megahertz here. So they are marking it as 400 here. So in this way, they have designed the database here, and those database have been used in the design part here. Similarly, for the both the bands, the figure of merit has been prepared here for 2.4 to 3 gigahertz and 5.15 to 5.6 gigahertz bandwidth here. So based on the parameters, we have to select certain parameters. What they have already selected, so we have considered here. These are design parameters in the design itself. Then next part was go for the model training. Then again, we have to split the data in the 80 and 20 ratios for the testing and the validation part. Okay. And then figure of merit part we applied. These are certain values. Okay, mean square errors, you can find out what is coming in case of NN. You can observe that's the minimum we are getting in case of NN here. So it shows me chances that NN is slightly performing better compared to the others here. Same is being reflected into the graphical representation. And these are the some of the results once we are going for the validation part. So whatever the actual simulator is giving to us and what the model is being predicted in it here. So that was for the reference purpose. So actual and the simulator environment, if you see, both are coming in very close proximity. So this close proximity shows the model is able to learn the features which we are trying to inculcate to the models here. Okay, so that part was done very nicely. These are the certain values from those learning part. Then for the improvement part here, we have used another method that was trust region optimizations. Again, the same process, same figure of merit, same data sets have been used for the new algorithm. Then we have run the models here on the basic database, certain iterations, then certain predictions related to the values here. And end of it, once we compare it here, then it was giving us slightly better, correct, compared to the previous one here. These are a few more results related to the analysis part. Internet design. Okay. So ultimately, once we compare it, whatever is already cited in the literatures, compared to that is slightly better. Using the ML techniques, the advanced ML techniques, we are able to perform it here, achieve it here. That given us the advantage here. That's we can move ahead for some other designs here. So in a nutshell, if I say earlier value was close to now 22 dB, we were able to mark 32 dB here. The bandwidth, total bandwidth figure where it was 2.6 gigahertz approximately, we were able to achieve a 3.3 gigahertz bandwidth here. So these are certain milestone which we have achieved very easily here. Okay. So that was the better results in terms of what is already cited in the literatures here. That shows the power of algorithmic solutions or AI tools here if we apply in a proper manners here. The way we need to apply them here, for application of them, we need to understand the basic frame out first here. If we learn the basic frame out, then it's going to be helpful. Another interesting area is duplex antennas, okay, where these structures have been also considered, where the number of parameters were more as well as the complexity in the design were more here, just for the replication purpose. Design parameters, few of the values, data sets values. Okay. So once you go for the parametric analysis, large number of data set will be generated. So it will take approximately 12 to 24 hours for the generation part here based on number of parameters being selected. And what are the actual parameters? What are the predicted values here? There's a difference in terms of theirs. We have just calculated and then we find out this is going to be better here. There is another interesting work which I want to discuss with you all is CNN based inverse and forward networks for antenna design here. So the idea is very interesting because once we go for the designing part here, we are always looking in terms of parameters here. So based on those parameters, we are observing the results here. Okay, and then based on the results, we are trying to conclude it that the structure is optimal or not it here. Okay, what about if I go for the reverse engineering here? Reverse engineering, what if I decide already these are the certain areas in the design? Okay, if I exploit those section only here, ignite those section only here. The first is efficiency in terms of space. Second, in terms of power resources optimizations here. So those parts of the structure which are predominantly contributing in the radiation here. So I can think for those segments only here. So these way, the thought processing was that here. Because if I see the overall structures here, whatever the radiation characteristic bandwidth, I'm getting it here. If I see the structure here, there is always a surface current distribution here. So based on the surface current distribution, we can always get an idea that this segment is contributing more in the radiation or this segment is contributing less in the radiation here. So if I want to go for the reduction in the structures here, then I will prefer those area where the surface current distribution is not too high. Okay, so this kinds of optimizations, if I can perform from the structural point of view, okay, then comes to the final design. Okay, so just a genetic algorithm framework. So data was created. This part you can understand from here very easily. Okay, so this is the one of the layout. Just I have slightly zoomed it for your reference here. What we have done, I have break it into a grid of 20 cross 20 here. I think 15 cross 50 it is. 4, 6, 6, 10, 12. It is 12 cross 12 here. So in case of 12 cross 12 grid, there will be 144 grid here across the structures here. Out of these 144 grid, if I change the feed point, accordingly the overall contribution is also going to be changed. Okay, and simultaneously I can find out based on the changes feed here positions. Obviously, the radiation characteristic is going to be changed here. That's quite possible because based on the change in the surface current. The moment I change the feed position, accordingly surface current distribution across the layout is going to change. So accordingly, overall radiation characteristic is going to be changed here. So that is very fundamental part here. The point is, if I am changing the feed, so accordingly I can reconfigure the overall characteristic of the structure here. In place of optimizing the characteristic here, I can optimize the positions values here based on the surface current. Now the point is how I can simulate or mimic this kinds of design thoughts in the overall algorithmic solutions here. It's slightly tricky compared to the previous approaches, two approaches which we have discussed it here. Then here comes the genetic algorithm solutions very handy. If you remember, once we are talking about the basic framework of the genetic algorithm, we have discussed the two ways. One is genetic algorithm can work on the absolute manner, on the absolute number. Second is genetic algorithm can work in the binary manners here, binary number form here. So once it is working in the form of binary, it could be in the form of 101010, etc. and so on here. Once it is in the form of 1010, correct? Then I can mimic it. Just those are coming in the purple region could be mapped with the one, and those who are coming with the white region here could be mimicked as a zero numbers here. So once we have this one and zero form here, now I have the chances for me to think of a genetic algorithm binary form of representation here for my overall structures here. Did you get the logic? Because logic is very important. Once you connect with the logic, rest design is very easy. Okay. Idea was in a nutshell, overall radiators I have divided into the genetic into a grid of 12 cross 12. That's a 144 grid you can find out here. And for igniting purpose, I can say I have used a slight trick. Right? That is 1010 form. I'm going to use it. So binary form of genetic algorithm could be a more appropriate for me. So the purple one, which is reflected, I can mimic it with the one, and the white one, which is not contributing here will be mimicked with the zero numbers here. So the purple one could be considered in the overall structure as a metal part, and the white structures could be considered as the part which is not radiating it here. No metal part here. So it is up to designers how we are going to frame the problem. Accordingly, you can optimize it here. Okay. But these things can be done very easily here once I apply the genetic algorithm. And in case of genetic algorithm, for generation of the data, we have the processor in the simulator environment here. If you explore the simulator environment here, you can generate the data. So this is the framework I have considered. Okay. So nowadays, if you see the most of the simulators which are coming out with the genetic algorithm module as a one of the optimizers part here. Either use the CST, CST have this provision it here. And once you have generated the data, we'll try to mimic it. Then certain algorithmic solution like CNN, LSTN, and MLP, we have tried it, and based on that, we have tried to frame it, and then we have considered the values which is coming it here in all the three cases. So once you have cross validated here, it was coming, all of them are coming in the close proximity range, but however the MLP was performing slightly better to them here in terms of overall performance it here. And there were certain other functions explorations, ReLU we have explored, right? And then actual values, ground truths. What was the GT? GT is here for the ground truths. So whatever the predictions is being done by the model is the same structure, same way if I start doing in the simulator one here, because based on the configuration of the selected 1 and 0 form by the simulator one here, there will be corresponding S parameters here. Okay, and similarly I can mimic this part in case of our simulators, and then we will try to generate the S parameters here. Are these two S parameters are very close to each other here, or simulator is performing slightly different what we are getting it here. So once we try to cross validate here, so both are the results were coming in the very close proximity of each other, a close range of them here. So here again the desired range was covered in both the cases here. Okay, so what is the ground truth is giving and what is the model is predicting here. So model one you can observe this range is perfectly covered in both the cases here. So what is the model is predicting? That is acceptable range here. So but the catch is now if someone asks to design such kinds of structures here which have such kinds of reconfigurability or the tunability here, because these kinds of structure is going to be more and more demand once you're talking about the 5G or the 6G system here, where reconfigurable beamforming concept is coming it here. So for the reconfigurability, we have certain advantage in terms of amplitude, certain phases here, but can we bring those reconfigurability in the design part also here? So that is cross validated here. Another example, I think, okay, let's cover it very quickly. Another design part, there are certain design I have considered here. So where SVR and XGBoost we have considered it for the design part. So original SVM support vector machines, then cross validation with the models here, whatever we have generated to the simulator similarly has been cross validated here. Then the random forest part. Then if we compare with the random forest XGBoost here, so we are clearly able to mark it. That's XGBoost is performing slightly better compared to the previous one here. Another part, we can explore it with the meta surfaces, the previous design with along with the meta surfaces. I can go ahead. So meta surfaces was going to give us the more increment in terms of bandwidth here, because whatever the bandwidth you are getting, this was slightly narrow band here. If I want to increase it, the operating bandwidth here, I can go ahead with the enhancement here. Mhm. Okay, as parameters, another example is okay, deep automotive radar. So we are closing the time, so I skip this example. Yes, this will be something more important to us for exploration purpose, as I have discussed, using the case of CST, where the genetic algorithm-based data generation part, as well as some other algorithmic solutions part is available. The same part, those who are working in the HFSS here, they can also explore it. Okay, and once we go to the desktop part here, so there is well equipped facility here in case of HFSS nowadays. Okay, if you go on the automation module, so there you can find out the spaces. Okay, so there are multiple ways I can go ahead with here. PyEditor consoles here or the Jupyter notebook. If you have the code, the script you have, you can directly upload the script here. Okay, the script, and then you can start working on it here. Or similarly, if you want to code starting from the sketches here or design it here, then we can go with the Jupyter notebook here. So that part is also enabled here. So both are working very fine in the Python module. For a design control you want to obtain it here, those parts can be done very nicely here, especially related to the fractal antennas part if you want to do something here. So that part is very easily incorporatable here in this case, right? So with the help of design, this can be done it here. Once you upload the code or once you start writing the code here, multiple tabs you can prepare it, multiple designs you can prepare it simultaneously. You can run the design it here, code it here, and you can generate the design very easily. You can control the design parameters here very easily here in the simulator environment itself here. So nowadays, simulator is coming to be more and more friendly and more you can say interactive compared to what it were in the past here. So that is the my submissions here. And those who are willing to work in this domain, obviously there is a huge potential as a huge possibilities nowadays here to explore it. Similar exercise I can demonstrate in case of the MATLAB also here. Either you are working the CST, HFSS, or the MATLAB here. All these popular platforms have the capabilities to include the coding part here. There is a scope where you can start designing the system here with the help of code part here. And believe me, once you start interacting through the coding environment, you will find out it will be much more convenient and faster compared to our existing conventional approaches what we have followed it here. Because I'm more confident in saying these statements because I'm also coming from those old schools where we have done the work on the simulator environment here, the simulators here. At that time, we have not been exposed much more to these kinds of algorithmic solutions here. So I have well experienced how much time it is going to take, what were the pain we as a designer we have to take it in the design part here. So just to start it, you need to understand the basic Python part here. If you are good in the Python, if you learn the Pythons here, then the possibility for you to understand, explore is becomes much more convenient here. If you're not in the Python, then if you know the MATLAB here, so in case of MATLAB, you can run it. Go ahead it here. Maybe some other session we can have a discussion with the some hands-on session also here using the AI tools here. Okay, these are some references. Okay, thank you. If you have any questions, please feel free to ask me.
Thank you, sir, for delivering a special talk on AI in antenna. Participants, if you have any doubt or query, you may ask the sir on the chat. Sir, there are some participant doubt here in the chat. We will take them one by one.
Okay, sir, can we apply the PSO to microsphere antenna design? If yes, then how? Correct. Particle swarm optimization PSO. I think if you use the CST, they have already inbuilt it here. Okay, as well as in the HFSS, if you want to it here, I have just shown the interface. You can find out the code it here, and based on your design part, you can customize it and you can run it in case of HFSS here. So these part is nowadays available it here. So answer for your question is yes. Again, question is I hope I have answered it. If you still have some query, you may again write it down. Second question is how would we choose optimization algorithm here? So once we go for the optimization algorithm here, we need to see the complexity of the design as well as the resources available to me here. For example, if I'm looking for a simple patch antenna design it here, where the number of parameters or complexity is not too high, I need not to go for the hi-fi deep learning based approaches because deep learning approaches will consume your computational resources here, correct? And if you don't have such a high-end workstation here or server-based computational facility here, if you want to work simple your base station here, simple structures here with a good amount of time, then you can start with the simple regression techniques also here. Random search based approaches you can find out here. So random search is one of the quick approach here, or if you have certain better, then you can go with the genetic algorithm also here. Okay, so these kinds of tools are not going to consume a lot of competence resources. Yes, they are going to take a slightly more computation time it here compared to these techniques here. So it is just a trade-off based on the design complexity here. If I'm increasing the design complexity, then obviously I have to go for the more complex structures here. Like if you've seen few of my examples here earlier, there was a KNN SVR. I have used it. Later on, I have switched to the XGBoost here, where I use explicitly for the genetic algorithm based solutions, especially in the binary form here. Because dealing with the large data here, deep learning algorithm are more efficient in terms of result prediction here, but obviously you have to uh, invest something in terms of optimization resources here, computational resources it here. So that part you need to manage it here. Okay. Which optimization algorithm is best for antenna design? I think already answer is third query. Which tool should be used for AI or ML optimization? NF, is there any book for detailed study of algorithm? Okay. So for the tool perspective, if you ask it here, HFSS is already providing the facility. CST is already providing facility. I've already explored it personally myself here. And MATLAB, we have already explored it here. So I'm well aware about these three simulators here. So if you're working on other simulators, I'm well sure they also have some provision, because in this competitive environment they can't run away from these kinds of modest approaches of optimizations here. So basic optimization parts you can always perform within that your uh, algorithmic solutions which is availability here. But one part you must understand it, whatever they are providing the algorithmic solution, that is in generic form here. So how generic form is going to suit your application, again it is subjective. So once you are working on a specific problem, you are not customizing as per your need it here, it is not going to be that much effective. So I suggest please go ahead with certain detailing here in the design parts. Or related to the book or detailed study of algorithm here. So the first thing I suggested, you all learn the Python programming or the MATLAB programming, which we are very comfortable. Okay, and once you are comfortable with that part here, then you can find out the information bits and pieces here and there, and then you have to compile them here by yourself here. Can you please suggest how to proceed, sir, as a newcomer in the design area, but he has domain theory knowledge, sir? Okay, for domain knowledge, or if you're really willing to start this work here, if you're not able to find out enough resources, all of you are most welcome to our lab here. We always welcome the interns as well as the MTech students also, PhD students also here to work in our lab here. And we have also good resources, as well, not only the simulator environment but also the fabrication facility we also have. So if someone is willing to learn explicitly here, he or she is most welcome to come at Triple IT in Raipur, and we will definitely accommodate you to guide you here in this learning process here. Anything else? Any other
Sir,
questions?
any other doubt, participants? Okay. Thank you, sir, for delivering such a special talk and taking all the participants' doubts seriously. Your insightful presentation and valuable contribution greatly enriched the session and provided the participants with a deeper understanding of the AI in antenna. We truly appreciate your time, effort, and willingness to share your expertise with us, sir.
Thank you.
Thank you. Thank
Thank
you,
you.
sir, for your time.
Okay, thank you, Dr. Sarsak, as well as the MNIT Jaipur here for connecting with all of you and sharing with my expertise in this domain here. Thank you once again to all of you.
Okay, participants, this session concludes here. We will now take a lunch break, and our next session will begin at 4 p.m. That will be your hands on session. Thank you all.